So, hey guys, welcome back to Mechanical Training for RoboJackets. Today we're going to be talking about one of my favorite topics, which is like some materials sciencey stuff, so you guys understand how to choose stock and materials for you to actually use in RoboJackets and anything that you design. So, stock, steel, and strain, as the name implies. All right. So, what are some of the considerations when you take when you're actually selecting a material for an application? So, like obviously, we're going to be throwing around a lot of like, oh, let's use aluminum for this, let's use some steel for this, let's use some PLA or some plastic for this, right? But they each have their own applications and their own uses. So first and foremost, like the one that you're going to consider the most, right, is cost, right? There's a reason why concrete is used everywhere. It's just one of the cheapest materials and it has a really good compressive strength. So that's why you end up seeing it just everywhere. Obviously, the weight and the density of the material is going to matter as well, right? Specifically with like airplanes, you can think about like most of them use aluminum, and actually some new ones like the Boeing 787 started using some composites like carbon fiber for a pretty good chunk of the aircraft itself, just because their strength to weight ratios are insane, and those weight savings can go a long way, especially in those applications. And how this kind of applies to RoboJackets itself is when you think about like BattleBots specifically, or I'm not sure if RoboCup has weight restrictions, but essentially like if you have some metric like with weight that you're trying to, I guess, design towards, like, you have like 3-pounders, you have 20-pounders, 30-pounders. I'm not sure if those are the right numbers, but essentially like with those specific applications, you're going to want to choose materials that are good at what they do for those specific weights. So that's like those two are some pretty good ones that you have to consider. So other ones are like application requirements. So like for an example, like friction. In RoboNav, the material that we use to coat the battery boxes is actually a plastic called HDPE, and we use it just because it has a very low coefficient of friction. So that way we can pull the batteries in and out like super seamlessly, right? And the other one, which is like super important, is response to stress. Obviously, I'll talk a little bit more about what stress is and, from the name of the presentation, strain is in just a second. But those are incredibly important, and you're going to be studying that in 3 or 4 classes in your undergraduate degree if you're at ME or aerospace major, right? And the other thing is like that's really important, especially with manufacturing, is how do you intend to machine it? Obviously, like if you have a huge sheet of metal that you have specific operations that you're kind of constrained to, as opposed to like if you're 3D printing something, you're going to have a lot of those restrictions taken away. You're a lot more free to do stuff with it. So yeah, that's kind of like the basic ideas of what we do when choosing material, especially in RoboJackets. All right. So what exactly is stock? So I kind of mentioned like sheet metal before, but essentially it's just like the starting piece of material that you're going to be using to like actually become the part, right? You're not just going to create a shaft out of nowhere. You're probably going to have to use a piece of round stock and then cut some, what's it called? Do whatever you want with the stock. You can add threads to it and whatever, but you're going to have to start with some material itself. So stock geometry is always going to be like a primary consideration when you design the part. And eventually, like once you start making part orders and that stuff, you're going to have to start looking at like what specifically is available to you with like online metals. Midwest Steel, I think, is another one that we use. But essentially, like each of them are going to have their own options, and some of them are going to be a little pricier than others. There's also different methods of creating that stock. So like, for example, on the right, we have extruded sections. So essentially like, remember those Play-Doh things that you might have played with when you were younger, right? The ones that like make like little noodles and different kinds of stuff. That's exactly what goes on in extrusion factories. They're just playing with Play-Doh, essentially. They're taking a piece of like molten metal, usually like aluminum or steel or whatever, and pressing it through an extrusion of the shape that you're working with. And eventually that turns out into that piece of stock that you want. So like that's what you get on the top right. You also have, for example, like hot rolled and cold rolled sheet metals. So what exactly that means is like in hot rolling, when you're actually flattening out the part, they have these huge rollers that are applying pressure to the sheet metal itself in order to make it thinner. And essentially, if you make it, if you do the rolling operation as the metal is actually heated, then essentially you're not going to have issues in terms of material structure, and you're not going to have what are known as residual stresses. So that's what's really important to note with when you're deciding between hot rolled and cold rolled. And As a consequence, oftentimes hot rolled becomes a lot more expensive because the energy input required to heat these huge pieces of steel or aluminum or whatever is going to be quite pricey, right? It's not cheap to keep the heating on. So that's why we generally use cold rolled steels for those kinds of operations, just because it's a lot cheaper, and it, honestly, like the drawbacks of using cold rolled aren't that significant, in my honest opinion. All right, some other things to consider with stock is like materials will come with different cross sections. I did mention rod stock when talking about shafts and threading them, right? So rod stock is literally like you have a circular cross section right over here. You have sheet stock, which is what I was talking about with hot rolled and cold rolled. You have plate stock, which is honestly the same thing, except it's a lot, I guess, smaller, right? Sheets will will be usually like pretty wide and pretty thin, whereas plates are going to be a lot smaller. And the same thing with bar stock, honestly. Okay. Am I going too fast, or is this good for you guys? Just want to check real quick. All good?
Seems good.
Okay. Sorry. I'm excited about this, so I really like talking about these materials. Okay. All right, cool. So when specifically choosing some materials, right? Some common ones that we choose are aluminum. And what you need to know about aluminum is it's a lot less dense and lighter than steel. Typically, steels come at, I think, 7,200 to 7,800 kilograms per meters cube. And aluminum, okay, I don't know at the top of my mind, but trust me, it's a lot less. Okay. It'll be more expensive than steel, but it's also really easy to machine because it's a lot more pliable. And some alloys to know specifically are aluminum 6061, which is what you're going to be using for the most part. It's a lot cheaper. It's probably the most widely available material out there. It's used in airplanes and all that stuff. So it's really easy to machine. Aluminum 7075, for example, or on the other hand, is almost as strong as steel, but it's a lot more expensive. So again, really depending on what you're planning on choosing, right, and what budget restrictions you're working with and what kind of loading conditions you're working with, sometimes aluminum 7075 is going to be a little bit more apt for you to use. And again, that's used a lot in aerospace industries. Something to note with aluminum specifically, like those alloys, is you'll notice here, right, 6061, a lot less strong than 7075. Typically with the aluminum series, the lower the number, the more ductile but much weaker the material is. And yeah, that's just something to keep in mind. Like from the top of my mind, I can remember RoboNav using, I think, aluminum 5052 or something like that for some of our sheet metals, just because those were very ductile. We were planning on bending them, so it was a lot more ductile, and it wouldn't break during those bending operations, and it wasn't going to go under significant load. But yeah, hopefully that should be good enough for you guys to understand what kind of makes aluminum special. All right, some other materials to work with. Steel is the big one. As like everyone kind of knows, it's a lot stronger. It's a lot than aluminum, but it's also a lot more time consuming to machine than aluminum, and it'll take a lot more. It's also a lot more ductile than aluminum, so it'll take a lot longer to break in terms of strain. Some commonly used alloys are A36 steel. So that's like your standard like steel. It's used in structural applications and it's super cheap. I think they use A36 in a lot of I guess construction, just because it's very cheap and it's very strong. There's also S7 tool steel, so it's heat treatable to very high hardness. And there's also AR 400 and 500 steel, and it's very impact and abrasion resistant and also bought heat treated. So when we talk about heat treatment, that's usually just means like they specifically heat and cool the materials themselves to be to have specific material properties. If you've ever heard of like Forges of Fire, I think it's called. Like there's a series on YouTube that specifically deals with like what's it called? Blacksmiths making like famous blades. Like they'll go into a lot of the metallurgy and a lot of the heat treatments they do to the steels to make them really strong. All right. But yeah, those are the difference between all those alloys. Okay. All right, plastics. This is a whole nother ball game. And as you can see, this guy over here is very angry. So don't make the plastics too upset. All right, they may be weak, but they have their own uses, okay? All right, so choosing some material with plastics, right? The most commonly used ones in RoboJacket specifically are ABS and PLA. So something to note about ABS, it's 4 times more impact resistant than PLA. So if you're in BattleBots, that might be more useful for designing drums and stuff. I'm not entirely sure. I haven't really used it for those applications, but it's also prone to warping. On the other hand, we have PLA. So it warps a lot less and can form sharper corners, and it's a lot easier to print. It's biodegradable, but it's also a lot more brittle than ABS. And something to note is for PLA, it's a lot more, because it's biodegradable, or the reason it's biodegradable is because in environments, if you like leave PLA outside, it'll actually degrade out in the sun. So that's why we don't typically use a lot of 3D printed stuff that needs to be going outside. Or if we do print stuff out of PLA, we plan on replacing that in the worst of cases, Oh, and again, and another thing to note about 3D printing specifically is you need to be mindful of how you're printing the material itself. So it's going to be a lot weaker in shear, and it's going to be pretty strong in compression, just because each of those fibers or each of those lines of filament that you're printing out aren't going to be perfectly bonded together. So those like imperfect bonding are going to be sites for you to, I guess, begin propagating cracks and start weakening the material itself. So you do need to keep the way you 3D print it in mind in case you run into, have some loading scenarios in mind that you want this 3D printed part to go under. Okay. All right, some other materials that we choose. Nylon. I think this one's used pretty often in BattleBots. The reason why it's so good is because it has a really high tensile strength, is very impact resistant, but also used in 3D printing, but not as often. I think nylon is used in a lot of stereolithography, but we don't have those in RoboJacket Studio, unfortunately. Another one that I mentioned way earlier is HDPE. That's a high density polyethylene, I think. And the advantage of using HDPE is that it's like lower cost. It's also lower density, but very flexible, and it's pretty ductile as well. And kind of what I mentioned before, like the specific application that we used it in RoboNav is that HDPE also tends to have a low coefficient of friction with the materials that we use, right? So that's a good reason to use those. All right. Now let's get into a little bit more of the nitty gritty of the material science. So stuff that you keep in mind with and where you actually do some calculations in order to make sure that your parts don't actually do things that you don't want them to do. All right. So we kind of quantify 2 different things. One of them is stress. So you can think of this as like an internal reaction to like external loads. And typically these are, this is normalized to the cross-sectional area that you're working with. So if you think about it like this, let's say you have a stick, right? The thicker that stick is, a lot harder it's going to break, even for the same force that you're applying. But if that stick is super thin and you start bending it, then since it's a lot smaller in cross-sectional area, you're going to have more stress, right? Because stress itself is equal to the force that you're applying over that cross-sectional area, and the units are newtons per meter squared. The other thing that we keep in mind with, and this kind of relates to ductility with what I was talking about earlier, is strain. So whenever you stress an object, you also cause it to strain a little bit. And essentially what we quantify as strain is just the change in length of the material or the part that you're using with respect to its original length, right? So like what you can see on the screen over here, right? Let's say you have these bars. It'll displace some dx for some force that you're applying, and you're going to compare that change in length to the original length, and that'll give you your strain. And because of this, you're doing a length over a length. This strain is going to be unitless. And on a final note, we denote stress as sigma and strain as epsilon. All right, now going over to what materials actually kind of do, right? So in material science, we typically look at the stress versus the strain of a material, right? So like as you increase the load internally to whatever material you're working on, it's going to start deforming, right? And the initial section that we talk about is called the elastic region. So in most materials, right, you'll have a pretty linear relationship between stress and strain. And, that ratio is called the Young's modulus, but I think we'll get to that in just a second. And what's important about that is that it will, no matter what stress you apply to it within this region, the inelastic region or the elastic region is always going to be able to redeform back to its original state. So I have a pen. Unfortunately, I'm going to have to sacrifice this pen for the name of learning. But if you think about it, right, you have this little metal part, and if I try stretching it for a certain part, it'll just go back to its original position. So that means this, I think it's probably aluminum or steel or whatever, is undergoing elastic deformation. So no matter where I am with the stress, as long as it's before that limit of stress, it's going to be able to go back to its original position. The following section, anything after that linear region, we typically denote as plastic deformation. And what's important to note about this is that the deformation that you're getting when you're applying stresses is going to be permanent. So like in my example, if I stretch this out a little bit too hard, let's see if this works. Okay, that's a little too permanent, but I hope you guys get the idea. Actually, in here you can see that there's some deformation that didn't go back to its original position, and that's because the material itself has undergone a change that it's completely permanent past that elastic region. And any deformation that occurs after it is called plastic, and it's permanent. So in metals, we typically look at the ridge in the plastic deformation section in order to quantify it, right? So for most materials like that are metals, like you'll get this little ridge over here. I think you guys can see my cursor. And essentially wherever we stop getting that relationship is where we'll say that it's plastically deforming, right? And the first half of the ridge, we have what is called strain hardening, just because the material gets harder itself before it can go back down. And then in the second part of the little ridge we get over here is something called necking. I think we'll get into that in a little bit. It's honestly not that big of a deal, but essentially the main takeaway from these graphs is that as long as you keep your materials below the yield strength or that limit that I was talking about before, or make sure that the material in your part is underneath the is in the elastic region of deformation, like you'll be good to go, and that's kind of how we quantify whether a material has failed or not. All right. Okay, so now breaking it down a little bit, I know I just threw a bunch of different names for all these things at you at the same time, but I'll go like one at a time and discuss what exactly all these things are. So stiffness is this external force divided by displacement. So like you can think of this as like whenever you apply a force to an object, it'll displace. So the stiffer a material is, right, no matter how much force you put it, it's going to displace very little, right? But if the material is not very stiff, right, so you'll actually have a lower slope over here. If the material is not very stiff, then if you apply a small force, it's going to be able to elongate a lot, right? You can think of this as like the difference between like a rubber and a steel. If you like stretch a rubber band, it's going to stretch a lot, right? But because it's not very stiff, whereas with steel, like unless if you're really strong, right, you're still going to have to apply a huge force in order to deform that steel, even the slightest bit compared to that rubber, even with the same dimensions. So flexibility, I've actually never seen this term, to be completely honest. It's the inverse of stiffness. Elasticity is the resistance to permanent change. The big one that you have to keep in mind here is Young's modulus. So kind of like stiffness, it's a ratio between two properties that you can think of like kind of intuitively. So on this curve over here, we have stress on the left-hand side and strain on the bottom, right? So as you increase the amount of stress in a material in the elastic region, right, you're going to also be increasing the strain at a linear rate. And the ratio between the two, or the slope of this area, is called the Young's modulus. And typically, like in that region, if the Young's modulus is higher, it'll also be stiffer as a consequence. And if the Young's modulus is lower, it's going to be less stiff, right? The other thing that you would want to keep into consideration, and this is typically what's used as a criteria for failure, is called the yield strength. So I mentioned that like a brief bit before. Essentially, the yield strength refers to the stress at which the material will start to permanently deform, right? So essentially, when you design a part and you do your calculations, and you'll probably have to ask your upperclassmen to help you out with a lot of that because it honestly gets pretty involved and it's a little complicated. As long as your stresses aren't going above that yield limit, like you'll be completely fine. And I guess another part that's important is called the fracture point. So even after a material deforms, it'll have a little while until it actually completely breaks off, like in my poor pen's example, right? And we call that just the fracture point. Obviously, honestly, that part isn't as important, but in a lot of cases like BattleBots, you'll typically see like after a couple matches, your material's already going to start banging up, but nothing has completely snapped yet. But then because of repeated loading and increasing the stresses when you're doing impacts, eventually it'll get to the point where it fractures and separates into lots of pieces. All right. Now, another thing that I described earlier is like a difference between like a ductile material and a non-ductile material. So I was talking about aluminum versus steel, right? With steel being a lot more ductile. A really important metric that people use in defining materials properties is the ductility. And it essentially just boils down to the area underneath the curve, or you can think of this as like the absorbed energy of deforming that material, right? So with more ductile materials, they'll be able to undergo a lot more deformation and be able to absorb a lot more energy before they break. But with brittle materials, as soon as they get to the yield point, they pretty much aren't going to be very useful, to be honest. And you can kind of think of this as like, in the case of this guy, it deformed a lot before it actually got to a point where it fractured, so it was able to absorb a lot of energy. But imagine like, obviously I'm not going to do it with this piece of glass, but if you apply like the same stresses and eventually get to the yield point, it's not going to be able to stretch a lot. This material is actually very brittle. So as soon as you get to that point, it's going to fracture like down the middle if it's like a dog bone sample, for example. So like something to note is that like the cutoff between ductile and brittle is pretty arbitrary, right? Like I'd call this piece of glass brittle and like that piece of metal ductile, but honestly, like they're usually used like relative to another, right? Like when we say one material is more brittle and one of them is more ductile, it just means like they have more or less area underneath their stress strain curves, if that makes sense. Now, why exactly is this important, right? So all materials will have a point after which they will start to plastically deformed and another where they will break and fracture when subject to a load. So when you design a part for any sort of loading condition, it's very important for you to like understand like what loads are it's undergoing, what stresses it might see either through like hand calculations or some computational solver. And essentially you want to keep your materials underneath that point where you're designing such that the loads that you're expecting it aren't going to cause this material to go into the plastic region. And what are these called? So like the yield point and the failure point, kind of what I was alluding to before. Now, when you design parts, you should also think about what type of load is being applied and where. And then you should adjust your design to give extra support in these areas. So like, for example, let's say you have this bar on the side and you want to start bending it. Since there's not a lot of, what's it called, area, cross-sectional area or like moment of inertia, like for that section, it's going to be able to deform quite a lot, and it'll obviously go under a lot of stress. So one thing that people do in these kind of sections is to add a little rib over here so that some of the load gets distributed to that, and you won't have as much stress when you're actually bending it. Another example is like you can add 4 bolts instead of 2. to hold a piece together more securely. And you can also add a puzzle fit specifically so that the bolts don't deform when you're actually applying them, right? Another thing why this is important is that this is of central importance when you're actually selecting materials. So you have to consider the ductility, the strength, the machinability, etc. required of the part and the design when you're considering the materials and the part's strengths and weaknesses. So just keep those in mind when you're designing something, right? Now, there's 4 different types, well, I guess 5 different types, but one of them is kind of similar to another. There's like 5 different types of loading that you can actually like see, and these are like what you have to take care of when you're designing stuff. There's tensile, so like when you think of like pizza cheese, right? I'm already getting hungry. I did not eat before this, so when you think of pizza cheese as you're taking the pizza out of the pie, these bits of cheese are going to be in tensile loading because they're stretching apart, right? There's also compression. This is the one that's a lot like tension. It's the same as tension, but just in the other direction. So instead of like pulling apart something, you're actually pressing it down. So you can think of like a stress ball when you're talking about that kind of loading. Another type of loading, this is actually fairly uncommon in my opinion, like from what I've seen. Like unless if you're designing for like bullets not to penetrate your object, it's not going to be as important, right? So shear is another loading condition you can think of. And like the primary example that I like to think of is when you're actually cutting something with scissors. You're actually shearing that material through, and you're taking into consideration the force that you're applying in this direction and then the area that's being applied perpendicular to that. So the other 2 loading conditions that you have to think of when you're designing a part are bending and torsion. So with my poor pen that I destroyed for the sake of learning, right? I was bending the material up in order to start deforming it. And you can think of this as like breaking a popsicle stick. And what's important about bending stresses specifically, and you'll actually see this a lot with construction materials, right? Is that there's going to be a lot of tension on the bottom, right? So if I bend this guy up like this, the bottom part is going to be in tension because it's being pulled away, but the top part is actually going to be in compression, right? Because you're moving some of the material inwards like that. And a common loading scenario that you see in real life is like when people design bridges, since concrete is very bad in tension, what they typically do is that if there's an element that's being deformed by bending, they typically add a what's it called? I'm missing the word for it, but essentially like they add a rod of steel into rebar. That's the word, rebar. They add rebar to the portions that are going to be in tension just to make up for that, the weakness of that material. And the last kind of loading scenario that we typically like look into is like torsion. So you can think of this as like wringing out a towel, and this causes a shear stress. So like what you see over here is like someone twisting 2 ends of like the towel itself, and you're inducing internal shears within the material itself to actually cause it to stress, right? So like whenever you're designing parts, you need to keep these 4 types of or 5 types of loading in mind, just so that when you're designing that part, it's not going to fail to those types of loading, if that makes sense. Now, I've talked a lot about material properties, but I've never really told you exactly how to find them. So the first answer that I give to anyone when looking for material properties is obviously Google. Like you can look up aluminum 6061 T6 material properties, and you get a bunch of them, right? But another one that I really like to use is called MatWeb, and like if you look up aluminum 6061 in Google, you'll probably just like find like 1 or 2 things. But if you look it up in MatWeb, which is like a huge database of different materials, you'll get a lot more than that. So you'll like get different strengths, different Young's modulus, different stiffnesses, like at different temperatures, at different conditions, and it's honestly pretty crazy. I recommend you checking out MatWeb. The other thing that you can do is ask another RoboJackets member since they've been using these materials for a lot of calculations, they probably know at the top of their mind. Like if you're designing something with like a regular piece of steel, right, probably like a mild steel, safe estimate of like the Young's modulus is typically like 200 gigapascals. And I'm sure like the people that you're working with in RoboJackets might know that at the top of their mind if asking them is a lot quicker than Googling it. The other piece of software that you can use, and this is in VLab under ME 2020, is something called CES EduPack. And what's really nice about CES EduPack, as opposed to like MatWeb, right? It is another database of materials, but you can actually use it to plot different materials for different properties. So like, let's say you say plot all the material properties of like Young's modulus versus yield strength for all the materials you have available in your database, just so you can choose some of them out for the application that you're working on, right? And that's a super, super helpful one. I highly recommend you guys look into that one. It's a fun one. So like now that we're done with kind of like the material sciencey stuff, I kind of want to talk about like our CAD tip of the day. So you might have run into this problem like last week, right? You might have asked us like, my part is in inches. You want this to be in millimeters. So in order to like change the unit itself, right? Since most of RoboJackets works in inches, other than I think RoboCup, if I recall correctly, you might have to change different units just for them. Or alternatively, when you 3D print, what's it called? When you 3D print, typically you're going to want to put them into millimeters because that's what the machine actually accepts as the unit that it wants to, it's expecting, right? Typically you want to stick with one unit for the same project, right? Like I said, like all teams use the same units except for like one or two. And you can go into, I think, iProperties. Okay, wait a second. Is this supposed to play? Hey.
It's just an image.
Okay, it's just an image. My bad, my bad. But I think an inventor, I forgot how to do this, to be honest, but I think you can go to like tools, options, properties, and then change the units for that, but you honestly won't have to for the most part. But just keep in mind that like when you 3D print stuff, you will probably need to change the units when you export them to your 3D printer. Now, for the specific 3D printer that we use in the RoboJackets shop, our slicer software named Cura uses millimeters only. So when you export, like I said before, you need to make sure that stuff's in millimeters and not in freedom units. All right. I hope you guys were able to absorb as much as possible. So today we're going to be doing a quick Kahoot so you guys can test your knowledge. And I don't think we have a prize. Typically in past years, we gave out candy in the middle of our lessons, but unfortunately, like, one, it's probably unsafe for me to give you candy like during the pandemic, and two, my arm is not that strong to throw you candy that quickly. So yeah, that's quite unfortunate. So if everyone can go on to Kahoot.it, and I'll give you the code in just a second. I'll share it on screen, and we'll play a little game to test our knowledge of what you guys just learned. Is everyone following?
Yes.
All right, perfect. So let's go. That is my homework. That is not what you want. Kahoot. Here we go. Okay. Once this pin comes up, you're going to want to put that in your device on kahoot.it, and we can get started.
I did test these over the summer to make sure that like all the questions asked are actually covered in the slides. Because there have been some questions in the past that didn't seem like they got covered right.
I'll probably just wait another minute for us to start, and then we can go ahead. Amazon Penguin 90, very nice. I also like the What is it? That's not a Lenny face, is it? I'm sorry. I'm really old. I apologize. I can't believe I'm getting out of touch with the youngins already.
Yeah, it is a Lenny face.
All right, cool.
It just looks a little different in the Kahoot font.
Yeah. All right.
How many people do we have? We have 21 who are not us.
Wait, there's 20 people on there. Okay, there's probably like one more person, so like they might just be thinking. Oh wait, am I dumb? Okay, there we go. I think we're all good to go. All right, you guys ready? Oh, where's the Kahoot music? I'm sorry. I'll put the Kahoot music on. Don't flame for this. Can you guys hear that?
No, it doesn't stream through your recording, unfortunately.
Oh, okay. In which case I'm going to put it down because it's actually really loud on my end. All right, let's go ahead and start. So the first question is, what kind of stress is this popsicle stick enduring? Right. I gave a lot of examples. I gave a sacrifice earlier in the name of science and learning. So I hope you guys remember this one. All right, cool. You got it. Now, for people that said shear or tensile, you are technically correct for like the underside that it is going under tensile stress, but the answer we were looking for was bending. All right, let's keep going. All right, Zach is killing it. Cura tick. Let's keep going. It's just question one. Don't get ahead of yourself. All right. Now, which kind of stress is being created by twisting the can open to get the sourdough out? Torsion. All right, perfect. You guys are killing it.
Yeah, technically shear is involved, but we're looking more for twisting means torsion.
Yeah. So the next question is, which type of stress is created by cutting the dough or tearing the dough to get the pieces? Shear or tensile? All right, very nice. Let's keep going.
Yeah, in your material science class, you'll find that tension does cause shear on the inside of things, but you don't have to worry about that too much.
Yeah,
tension
like
and
for
compression cause.
Yeah, tension and compression. Yeah. Like honestly, with a lot of loading scenarios, you're going to have a lot of phenomena going on at once. But what's really important is that typically in any loading scenario given, you'll have one thing being the primary, I guess, giver or the primary contributor of stress in that condition. All right, let's go to the next question. Let's stop hearing me talk. All right, what is the blue part of this stress strain curve called? It's blue boy. All right, you guys are killing it. Very nice. I'm starting to think Zach probably has a very fast internet connection. Everyone is killing it. But I'm not going to throw any more shade. I apologize. I'll stop imbibing with judgment. All right, what are the two materials that are most commonly used for 3D printing? All right, very nice, guys. Good job. That's PLA and ABS. All right, let's keep going. Blank equals reaction to blank.
Ooh, that's a tough one.
Yeah, I don't think I said this outright, but like when you think about it intuitively, it should kind of make sense to you. When you impart one, you will get the other. Very nice. Good job, guys. And sorry for not saying that outright, but you guys seem to get the idea. What is stronger, aluminum 6061 or 7075? All right, very nice, very nice. Keep going. Oh, this is neck and neck, guys. All right, let's see. All right, which material is more ductile, steel or aluminum? So here are the stress strain curves. Oh, this is a close one. All right, remember ductility refers to the area underneath the curve. Typically, we think about it like as a material is being deformed, it'll be able to undergo much more deformations for the same amounts of stress / the amounts of stress to failure. All right, let's keep going. All right, quiz time. Which is more impact resistant, ABS or PLA? Oh, I wasn't sure of that one myself. I was about to become a disgrace to the entire mechanical training community. I apologize, guys, but very nice job.
Yeah, the way I think of it is like the P in PLA stands for pretty because it looks really great, but it's kind of weak. I'm not saying that pretty things aren't strong, but like I had an acronym in my head for ABS that was like A stood for something. I don't know. I did some 3D printing over the summer, so I got a lot of experience with it.
The names I like to give ABS and PLA are acrylonitrile butadiene and polylactic acid. Yeah.
Right.
But that's just me, though. That's just me, though. All right, last question. Let's see who comes out on top. What is the name of the point at which a material begins to plastically deform? Very nice, guys. Good job. Good job. And now congrats to you guys. You guys no longer have to take MSc 2001.
Yeah, there's nothing else that's important in that class.
Yeah. Nothing else important. That's a joke, obviously, but please take it so you can graduate. All right. Okay, let's see who won. Third place, Nia Morad. Very nice job. Nikhil. All right, very nice job. And first, we got, drum roll, Kirtik. All right, good job, guys. 10 out of 10, 10 out of 10, 10 out of 10. I think this really did come down to internet speeds, I'll be honest. You guys were on top of this the whole entire time. Very good job, guys. And honestly, like, if you guys have any more interest in like material related stuff, or you guys really enjoyed this stuff, like, feel free to reach out to any of the trainers, or you can go ahead and bother any person on your team. All right, feel free. This is all in the name of learning, so it's okay. And 72% of you guys got everything, so very good job. That's a passing grade. I'll take it. Okay, so I guess now let's go to the CAD guide.
Yeah, here I can send the links.
Yeah. Just want to make sure that in my presentation itself, there wasn't anything after that. Yep.
Yeah, there's in the speaker notes of that slide, you've got all the links. So I'll just send them in the chat.
Right. Thanks, man.
So before we release you to like work on the guides yourselves, we're going to be doing or we're going to be looking through something related to CAD guides, but not exactly like a CAD guide. We're just going to be going over parametric CAD. It's just some good practices that you can have when designing things. So I'll send the slides for that.
Is there anything I need to share my screen for, or I think we're pretty much good, right?
Well, I mean, for these slides, yeah.
Okay.
And just kind of go through them.
Why do you not use Google Chrome? I just like Firefox. It's nothing crazy. Yeah, I like supporting my indie companies. Although Mozilla is probably not an indie company. At least compared to Google, it's a lot smaller. So, and personally, I don't see any performance change between Firefox and Chrome. But maybe I'm just oh, that's spicy. Well, it's not spicy because Chrome doesn't work for two-factor. But yeah, there you
That's
go.
interesting.
Oh my God, Brave browser. I've heard so many like YouTube advertisements and like YouTube sponsors like for Brave. I haven't tried it. Is it actually good? Oh, that's super rough. Holy crap. Wait, you can't use Honor Lock in Firefox? That sucks.
Yeah, I think it's like a Google Chrome extension.
Another reason to hate Honor Lock. I've heard so many bad things about it. Should I go on over to the CAD guide?
Yeah, so the first link,
Yeah. Cool. And I forget, are we breaking this out into different breakout rooms or
this is just like kind of part of the lecture, and then
okay, right.
Afterwards we'll just let them either stay and ask questions as they work through
right.
it, or they can leave and work on their own time.
Right. This isn't for them to follow exactly. This is just for me to teach. Right. Sorry. I apologize. Let's go. Okay. So let's go over some special topics with CAD. This is actually a super useful topic over here. This is used in a lot of RoboNav and IGBC and RoboNav and RoboCup specifically, I think. And I can tell you, like, from interning in industry, like, they use parametric CAD a lot. Like, this is super helpful stuff, okay? So why exactly do we choose to do parametric CAD? And I'll explain to you what it is in a second. It's to make CAD that's dynamic and is easily adjustable to different changes in design. So, like, let's say you're making a square part, right? And you have a limit to the perimeter, let's say, right? You can constrain each of the dimensions so that way when you make one change to one dimension, the other dimensions are going to change to meet that criteria, right? So another way to say this kind of, I guess, constraining in like this specific way is called parametric CAD. So the way that it works is you create variables with dimension values, and you can reference those variables themselves in like dimension prompt boxes, extrusion thicknesses, etc., wherever it's asking you for a dimension. And you can use that reference to start making equations to base your dimensions and stuff off of, right? So whenever you adjust the dimensions, like for one small part, and let's say that's for a variable name, right? Anything that is a function of that variable name is going to change as well. And you're not going to have to manually adjust those by yourself. Now, yeah, that pretty much covers it. Now, what parametric dimensioning is itself in like an inventor, so it'll let you make reference dimensions and variables and call upon them to make equations that are going to drive new dimensions. You can imagine this is a very powerful tool which will help you expedite the design process, just provided that you have a basic understanding of how you want to constrain certain dimensions to relate to one another. Like, for example, you can specify that you want one side of a rectangle to be named length and the other side to be equal to 2 times length. And when you change the lengthy boy, right, it'll change the 2 times lengthy boy as well, all right? And if you don't know that you want that side 2 times length is to be, right, then don't set it as that. Just use a standalone value like 3, right? It really depends on your application. So let's go over how we actually create those new variables. So whenever you dimension stuff, right, you have a dimension pop-out box. You can call that dimension itself by a name, right? And just like in programming, like if you're doing MATLAB or like Python and stuff, this will, what's it called? This will assign this variable top to whatever is on the other side, radius minus 0.25, right? But unlike in programming, right, like this will always happen. So once you change one thing, it'll continuously change the other things that are related to it, right? So you'll just name the variable equal to some other values, right? And you get another note that you can think about is like you don't necessarily need to give it a name. As you can see over here, like this dimension is called D12 by default, right? And all of your dimensions are going to have internal names to like the program itself. So you can in fact just call this like let's say radius is like D0, okay? So you can say top equals D0 minus 0.25, so that way you don't actually have to go back and name D0 radius in your assigning, right? That does get a little clunky, and it's honestly a lot better for you to understand what's going on here. And just like in programming, it's very nice for you to like have variable names that actually reference what they physically are, right? So like if you're saying radius minus 0.25, that radius better be the radius of this guy, right? It better not be the extrusion height, or else I'm going to be a little upset, okay? Like next slide. So when you create equations, just make sure that you know how you want that feature of your part to interact. So we could get the same value of 0.5 with numerous equations, but this one ensures that it'll always be the midpoint of everything, okay? And also note that this is an alternative to the first way that we made this initial point, which is like the midpoint of a construction line. So like in some cases, it's a lot better for you to just like name your variables and like call upon them in equations. But in other cases, right, like with this guy over here, since you're making it the midpoint of two separate, two separate radii, then it might be easier for you to go in a sketch and say like, let's define a line to be a construction line and put a midpoint and use that as the thing that you're constraining, if that makes sense. Now, the other part of parametric CAD that's super helpful, specifically is with Inventor, is that all those variable names, both the ones that you named and the parameters that are just like D0, D1, D2, whatever, right, are going to be in this one place called parameter box. Well, it's not actually called parameter box, it's just called parameters, but that's the name we're giving it for this, okay? So you can either find it on the top right part of, or the top middle, I guess, of Inventor, or you can go into Manage, go into this FX parameters guy, and this is where you can manage everything, right? So if you want to change radius instead of going into the part itself, you can just say, make this like 1 inch over here, okay? The other thing that you can do, which is not something that I've personally done, but other people on my team have done, is you can actually set up Inventor so that you can put everything into an Excel spreadsheet and then link it to a system of parts or some assembly that you're using to reference that off of. And it's really nice because then you can just keep everything in one little file and change things from there and then update. Okay. Now, other than just, what's it called? Redefining the things that already exist, you can actually add new parameters that don't necessarily have to be in the dimensions itself. So you can actually you can press add numeric, type in like the variable name, specify the unit, and put in the equation or the value and whatever, and you will have a brand new fancy variable for you to use anywhere else to reference, okay? Now, okay, so this is what I was kind of talking about / alluding to. It's a little different, but you can also link these dimensions between parts and sketches, right? So when you press link, you can actually share these dimensions themselves or in an Excel sheet, right? Between each other. So like, let's say you have a radius for like 2 different parts. Let's say you have a hole in this part and you have a shaft in this part. Okay, don't laugh. I know you're laughing. You can modify the dimensions of both just by going into that Excel spreadsheet or these parameter boxes after they're linked to change both of them at the same time. Boom, easy peasy. Okay. And what this link does over here is it'll just make those, global variables that are shared by everything. Okay. And that's pretty much it for the parametric section. I hope you guys learned something out of this. And now we're going to be moving on to the start part where you actually get to work on stuff. All right. Sounds good?
Yeah. So all you have to do is just click the links that I sent about 10 minutes ago. And so again, we have the CAD guide for people. And that CAD guide goes over sketches and a lot of different constraints that you can use. And the advanced CAD guide is just, again, for people who are either already comfortable with Inventor, who are looking for something a little more complex. or for people who are just looking for a little more practice, that's available to you. I think that this is the only other week with the advanced CAD guide. So yeah, this is something you can do on your own time. If you want to stay in the call as you work through it and ask us questions, we're totally open. But if you want to get off the call, then we'll see you next week.